Hello, everyone. My name is Tony. I'm a course advisor, and I will be your host for today's session. Before we start, I'd like to just give us some housekeeping rules. So these are notification and sound settings. So you are able to turn on and off the notification settings as you wish during this webinar. And please do post any questions under the Q&A function at the top right-hand corner. You will see there will be a Q&A at the end of the session. If the questions are regarding today's topic, our presenter for the day will be able to then assist regarding that. And just some frequently asked questions. So everyone registered for this webinar will receive a copy of the PDF slide and a link to the video recording within the next 2 business days via an email. So please do check your junk folder, spam folder, if the email does not appear in your inbox. And also, we will be providing you with a free digital certificate of attendance for live attendees. There will be a link and a QR code that I'll be sharing at the end of the session. Please, it does expire after 48 hours. So you need to at least claim it before that time. Just a brief explanation about ECT. So ECT is affiliated to the well-established Engineering Institute of Technology, EIT, is an engineering educational specialist. ECT delivers bachelor's and master's program. Our programs are designed by industry experts, ensuring that you graduate with a cutting-edge skill that are valued by employers. And also our program content remains current with rapid changing technology and industry developments. ECT is registered meeting the Office of Students requirement of course quality academic standard. Our lectures are subject specialists with industry experts, industry experience, and the required academic qualification. We also do deliver our programs via unique delivery methodology that makes use of live and interactive tutorials. The sessions are also recorded, and you'll also be given a learning support officer once you are enrolled into the program. Just event conduct. Please keep discussion lawful and respectful. Follow the chair for the chair's direction. Do not share illegal, abusive, or extremist content. Recording is not permitted unless authorized. Breach may result in removal and referral under the ECT policy. Today's topic is grid integration challenges, renewable penetration, inertia, and the rise of AI data center load. And our presenter for the day is Anand Otley, who she's also a founder and a CEO of Anand Global Advisory Senior Electrical Engineering. She's also a EIT lecturer. Hanan, you can then take control or then share your screen. Just a moment. Apologies for that. Wait, let me just. Are you sharing another? Okay, let me stop sharing mine. Okay. You know what's the issue, Hanan? Because I've already shared. Okay, let's see. You can unmute yourself. You're muted now.
Yes. So you can keep you can keep sharing the screen. Can you see the screen now? Can you see my screen?
Yes, I can see. Yes, I can see your screen.
Okay. Okay, good. So good morning, good afternoon, everyone, and welcome. Thank you to the Engineering College of Technology for having me, and thank you to everyone who has taken the time to join today. So this is the first session in our 5-part series, looking at the evolution of our modern power systems. So the title of today's session is Grid Integration, Challenges, Renewable Penetration, Inertia, and the Rise of AI Data Center. The reason why I choose this topic, because two major changes are happening to the power system at the same time. So if we look at on one side, we are connecting more and more inverter-based renewable generation, particularly solar PV and wind. On the other side, we are seeing a new class of very large, highly sensitive electricity loads driven by artificial intelligence and data centers. So neither trend is temporary, and we know that. So both are changing the engineering problem. So today I want to connect these two sides of the grid, the generation side, which is renewable energy resources or inverter-based resources, and in the load side, which is the AI, the data centers, because of the AI revolution. So, and I want to ask a practical question. How do we maintain reliability, stability, and resilience when both generation and demand are changing so quickly? So I will keep the discussion practical and engineering focused, and we will finish with time for your questions. A quick introduction, so you know where my perspective is coming from. I am an electrical engineer and the founder and CEO of HAN Global Advisory. It's an independent technical consulting firm based in Calgary, Canada. My work is focused on battery energy storage system, AI data center, infrastructure, distributed energy resource integration, grid modernization, and power system protection. My engineering background started in Morocco, and my professional experience has taken me across several regions, including Morocco, United States, Canada, Southeast Asia, Brunei, and Australia. Earlier in my career, I worked on high voltage and medium voltage substation with ONE, its National Office of Electricity in Morocco, that does generation, transmission, and distribution of electricity for the whole country. I worked mainly in transmission network dealing with protection and control. So I dealt with General Electric, Arriva, which is now Schneider Electric, and ABB protection relays. And also I worked on battery energy storage system projects in the US in partnership with General Electric Power Conversion. I'm currently finalizing actually my Master of Engineering in Electrical Systems at Engineering Institute of Technology, Australia. And my thesis focuses on developing continuous grid forming BESS control for resilient AI data center power. I also lecture in electrical engineering, and I work with MTP as the official global brand ambassador and strategic partner. So my interest in today's topic comes from both the power system side and also the immersion of intersection between battery energy storage system, grid stability, simulation, and AI data center. So before we get into the technical material, let me quickly show you how we will use our time together. So we already began with a short introduction and some context around why I work in this area. Then we will move into a high penetration of renewable energy resources challenges. And also, we'll dive into grid inertia and frequency stability. Like I want to make that concept or that connection very clear, because inertia is often discussed as an abstract concept, but its impact becomes very practical when disturbance occurs. So then we will shift to the demand side, AI data centers and why utilities are increasingly treating these facilities as grid-scale loads rather than simply another customer connection. Finally, we will look at how engineers study these interactions safely using simulation and modeling, including the distinction between RMS and AMT approaches. And I will close with key messages that I want you guys to take with you from that session. And then we will use the final 10 or 15 minutes for questions and answers. So let me frame today's discussion within a bigger picture. So you guys can have like a bigger picture and you will be able like to follow. So this is part one of our 5-part series on the evolution of power, of modern power systems. The later sessions, the later 4 sessions will take us deeper into battery energy storage system, protection, AMT simulation, digital substations, and grid-forming battery energy storage system. So today is intentionally broader. So I want to establish the system level problem before we start discussing individual technologies. So think about the grid as a balance. So when we talk about the grid, our power grid, we thought it's a balance between generation and demand. On the generation side, we have solar and wind are becoming increasingly important. And that's like from one hand, like it's good because for the decarbonization and greenhouse gases reduction, but they introduce characteristics that they are different from conventional synchronous generation, which are variability, inverter-based interfaces, and in many cases, reduced direct coupling between mechanical rotation and the electrical grid. So at the same time, on the demand side, we have AI data centers that are creating very large concentrated continuous load. So we have a generation fleet that's becoming more variable and electronically interfaced. While some new loads are becoming larger, more continuous, and more sensitive, we can see that that combination is what makes today's engineering challenge interesting. So the question I want you guys to think about is not whether renewables or AI data sensors are good or bad. The question is how do we engineer the system around them and make our power grid help our grid adapt to these changes. So let's start on the supply side. Which is renewable energy resources. So when it comes to renewable penetration, as I said, it's increasing rapidly, and that's fundamentally changing the generation mix. So when we talk about renewable integration, it's important not to reduce the discussion to simply adding megawatts of generation. So the problem is not just generate more megawatts of energy. The engineering question is what happens to the operating characteristics of the entire power system as that generation mix changes. So we will look at 3 connected issues: the growth of renewable generation, the variability of renewable output, the operational challenges that appear when penetration becomes high. And the most important point to keep in mind is that a grid can have plenty of installed generation capacity and still face stability and operational challenges. So let's start with how the generation mix itself is changing. So as you see in this slide, so you see that chart give us the big picture context. So solar PV and wind have moved from being relatively small contributor, as we see here, that the navy and orange lines, So they moved from being relatively small contributors in mini power systems to becoming major components of the generation mix. That transition is positive from an emission and energy transition perspective, but from a power system engineer perspective, a change in the generation mix also changes the physical and operational characteristics of the system. So the traditional thermal and hydro plants are generally dispatchable. Operators can control their output within operating limits, and also conventional synchronous machines contribute physical characteristics such as rotational inertia and fault currents. However, solar PV is different. So the primary energy source is variable because, as you know, we don't have the sun all day. We only have it like during the daytime. During nighttime, there is no sun. And also when it comes to wind. So the wind is available. Power depends on the wind resource. Yeah, and also we have another constraint or another challenge, that the electrical connection is through power electronics. As we know, like PV generate DC, so we need inverter to convert DC power to AC power, and also for wind.
To interrupt you. Okay, I'm having an issue here on my side. So it keeps going back to the first slide, the grid integration challenges. It keeps on going back there. But I see it's moving on your side, but on my side it's still at in the beginning. And I'm the one who's recording, so I'm not sure if the recording is going to appear this on my side, or is going to appear, your slides are going to appear on the recording. But yes, so I can see slide 6. So I think also the attendees, they can see slide 6. And I see
Can
that
you
you
ask?
are not. Yeah, because the issue, I think the issue was, let me just quickly check if I can do something about it.
Yeah, can we confirm this with the attendees in the chat box? Can you guys confirm if you can see the slide 6?
He was on slide, so because I see that you're on slide, let me
6.
see, 11, not 11.
11,
Are you on
yeah,
the
from side.
at the chats?
Yeah.
Yes. Are you able to take control now? Don't share. Just take control of the slides. Because if you share, it's going to then
Yeah, I
inter,
can take
inter
control. I
or
can
to
take
take control.
Yeah. So I can. So are we okay now?
Can you take control? Because I think you haven't
Yeah,
taken
I can.
control.
I can take control. Yeah, I can take control of the slides. So I am in the slide 11.
Slide. Can you move to 12? I just want to see something. If it moves on my side.
Yeah, I can move to 12.
Okay, it hasn't moved on my side. Let me see what's happening here. Yeah, because the issue is that if you share and I share, then it's gonna mix up. It won't. You're gonna see something different to me. Let me just quickly
Okay,
check.
so what we can do something. I can stop sharing, and you can keep going.
Stop. Yeah, you stop sharing on your side. Then
Yeah, let's stop sharing.
on your side,
Yeah, it's not. I'm not sharing.
you stop sharing.
Yeah.
Okay. Is it okay? Are you able to take control now?
Yeah, I am able to take control.
Can you take control? So I just wanna see. Because on my side, it still says that I am in control.
Yeah, so I can take control. I am
Okay,
on the slide 11.
Slide 11.
Yes.
Okay. Okay, because it doesn't give me. Let me see if I can give you control.
I have control. I can move the slides
Because
up and down.
on my side it doesn't move. I'm on 11. I went to
You
10. Can you
can.
see? Can you see that I went to 10? Slide 10 on your side. Can you see
No.
it? You
So
can't
what
see
you
it.
can do, take control. Take control and take control, and then I can, when I tell you, for example, next, you can go to move to the other slide.
Okay. 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 Can you hear me? Hello, Hanan. Can you unmute?
Hello?
Hello. Yes. Okay, did you take control now?
Yeah, but I can't see the slides.
You can't see the slides.
No, I can't.
Okay, let me see if okay, let me stop sharing. Then I'll share again. Just a moment. Ooh, let me share a new. Apologies, everyone, for the technical issue. We're going to be back just in a few minutes. We're going to continue with the webinar. I'm sharing it now. I'll just share it. Just a moment, still loading. Are you able to see the slides now?
No, I can't see the slides.
You can see the slides now.
No, I can't.
Let me see what would be the issue now. Okay, let me do this, right? Let me do this. Can you share yours? Let me stop sharing, then you just share yours.
Okay. Yeah.
Can you bring it to the screen?
Yeah.
You're
Can you guys?
You're 111.
Yeah. Yes.
Okay, perfect. Yeah, you can continue then.
Okay. Good. Where are we, guys? Okay, so let's. So as I said, so the question is not whether these technologies can provide reliable electricity. They absolutely can, and we know that. The question is how we maintain the system properties that conventional generation used to provide naturally. So the distinction becomes increasingly important as renewable penetration increases. At low penetration, the rest of the system can often absorb, these differences without major operational changes. But when there is high penetration of renewable energy, this characteristic of the renewable resources becomes system characteristics. So this is the transition I want us to focus on today. Moving from integrating individual renewable plants to managing a power system whose overall behavior is increasingly shaped by inverter-based resources. Yeah, can you move to the other slide?
It doesn't give you control to move.
I don't have that option control. Let's see. No, I don't have that option control. Yeah, if you can just move to the other side. I can just tell you next, and you can move to the other slide if you have the control.
Let me do this because I stopped sharing. Let me just then quickly share again because I stopped sharing. Don't stop sharing, it's fine. Don't stop sharing.
Yeah.
It's loading, just a moment. It's loading. You moved.
That's
I
okay.
see.
That's okay. I can move from here. Can you guys see
Oh, you can.
can you confirm the
Yeah.
slide 12? Renewable output is not really variable.
Yes, I can see that.
Okay, so yeah, that's good. So let's keep going. Now let's look at one of the most visible characteristics of the renewable generation, which is variability. So the solar PV output can change significantly over a relatively short period when cloud cover moves across a site. So at the system level, geographic diversity can reduce some of the variability, but it doesn't eliminate it. Wind behaves differently again, because wind generation depends on the weather patterns. So the wind can have like wind during different times of the day and different time of the year as well. So wind generation depends on weather patterns and can change over minutes to hours. Compare that with a conventional thermal generator. Within its operating constraints, its output can generally be scheduled and controlled by the operator. So this is the difference between conventional resources and renewable energy resources. So this matters because the grid has to maintain a continuous balance between generation and demand. So if renewable output changes, something else in the system has to respond. So that response can come from conventional generation, hydro storage, demand response, interconnection support, or other flexible resources. So as you see here, that variability itself is not necessarily the problem. Power systems have always dealt with changing conditions. The emergent challenge is the combination of variability, uncertainty, high penetration, and reduced flexibility elsewhere in the system. So that leads us naturally to the next question. What other characteristics become harder to manage as conventional synchronous generation is displaced? And I'm sure, guys, you know what it is. It's inertia. I will talk about that sooner. So when renewable penetration becomes high, operators face several challenges at the same time. The first challenge is visibility. What I mean, that a large amount of distributed generation, particularly rooftop PV, can sit behind thousands of individual customer connections. So from the system operators, perspective, not every installation has the same level of telemetry and controllability as a large generation station. The second challenge is central control. So utility cannot treat every renewable resource like a conventional dispatchable generator. Output is constrained by the available solar or wind resource and by the controls and interconnection requirements of the plant. The third challenge is forecasting uncertainty. What I mean by that operators can forecast renewable production, and forecasting has improved substantially. But weather-dependent resources still introduce uncertainty into day-ahead and real-time planning, because wind and solar, as we know, they are unpredictable because they are weather-dependent. So, and the fourth challenge is voltage and power quality. So a lot of distributed solar is connected toward the edges of distribution networks. Those networks were historically designed primarily for power flowing from like just unidirectional mode. that power flow from the substation toward the customers. Now with distributed generation, power can flow in both directions. So we have bidirectional mode, and that voltage management becomes more complex. The important point is these challenges interact. So you can have good forecasting, but limited visibility, and you can have visibility, but limited controllability. And you can have sufficient generation, but still experience local voltage constraints. So that's why renewable integration is really a system engineering problem, not simply a generation capacity problem. So now I want to move from the broader operational challenges into one specific physical characteristics that is very important to understand when it comes to our modern power system, which is inertia. This is one of the concepts that becomes increasingly important as conventional synchronous generation is displaced by inverter-based resources. So we will first define what inertia actually means in a power system. Then we will connect it directly to frequency behavior following a disturbance. And finally, we will look at why this matters for protection, grid codes, battery energy storage system, grid forming technology. So the key idea is simple. When the balance between generation and demand changes suddenly, how quickly does system frequency move? And how much time does the system have to respond? So what do we mean by grid inertia? It's a very important concept that we need to understand. So in a conventional power system, large synchronous generators contain rotating masses. The turbine and generator rotor store kinetic energy. So you can think of that stored kinetic energy as a physical buffer, right? So if a larger generator suddenly trips, a generation is no longer equal to demand. So the system frequency begins to fall, right? So the rotating machines don't need a control signal before they respond because of that high inertia, because of that physical shock absorber, because of that mechanical buffer, right? So their stored kinetic energy is already physically coupled to the grid, so energy is exchanged immediately as the rotor slows. That gives the system time, which is important. Now compare that with solar PV plants. The PV array itself has no rotating mass, has like no rotating mass connected directly to the AC system. Modern wind turbines do have rotational mechanical components, but the power electronic converter can decouple much of that mechanical energy from the grid instantaneous electromechanical dynamics. So that distinction is extremely important. I mean, it doesn't mean inverter-based resources cannot support frequency. They can, absolutely they can. But it means that the response has to be provided through control system rather than relying automatically on the same physical. So now when we talk about inverter-based resources, the control system becomes very critical and very crucial because of low inertia. That because of low inertia that synchronous machines has. So that's why we increasingly hear terms such as, I'm sure guys, you hear a lot of these terms like fast frequency response, synthetic inertia, virtual inertia, and grid forming control. So all these technologies are there to replace that high inertia that our conventional synchronous machines already has. So the technology can provide the support, but the mechanism is different. And once the system becomes heavily inverter-based, we need to understand those control interactions very carefully. So now let's connect inertia directly to frequency. As you see here, so imagine that large generator trips unexpectedly, right? So immediately after the event, generation is lower than demand. So the system has imbalance. So there is imbalance between generation and demand because our generator trips, right? In high inertia systems, as you see here, that navy line is for the traditional grid for the synchronous machine, synchronous generators, and that orange line is for for renewable penetration. So in high inertia system, as we see, the stored kinetic energy is in synchronous machines helps slow the initial, as you see here, it's helps slow the initial frequency decline. The frequency still changes, but the change is more gradual. In low inertia system, as you see here, the orange line, the same disturbance can produce a faster initial frequency change. So one important metric here is that the rate of change of frequency, which is ROCOF, that tell us how quickly frequency is changing. So the distinction matters because the first few hundred milliseconds, so this one is for like the first 30 seconds, but yeah, after a disturbance can determine how much time different protection and control system have to react. And that's the difference between high inertia, which is like for traditional grid, and low inertia for inverter-based resources. It's time, because that determine like how our protection and control system have to react. So it's not only about where the frequency eventually ends up, it's also about how quickly we get there. So that's why inertia is not just a theoretical machine parameters, it becomes a system level reliability. This is also one reason why conventional planning methods alone may not be sufficient for every emerging grid conditions. So why does lower inertia matter in practice? As I said, first, protection and control systems operate based on measurement of voltage and frequency. And also ROCOF-based protection can operate when the measured rate of frequency change exceeds a defined threshold. The intention is to protect equipment or disconnect abnormal conditions by protection actions. Also have to be coordinated with the overall system response. The second important point is that we now have technologies capable of providing fast response electronically. Like battery energy storage system can respond very quickly, and advanced inverter controls can be designed to support voltage and frequency, like grid forming technologies. So we need to provide the required system services in a way that works for the new grid. And that's why our next session will focus specifically on battery energy storage system and the technologies being used to address these emerging stability challenges. So we have covered now the supply. Now we're gonna cover the demand side of the power grid. One of the biggest shifts right now is the growth of AI, data centers infrastructure, because of AI revolution, right? So these are not just incremental loads. Their scale, concentration, and power quality needs create a very different planning problem. So now let's look at what's changing on the demand side. So as you see here in that chart, that AI requires enormous computer resources. So AI data centers, they are very critical loads that they consume a substantial amount of power because of GPU clusters and AI training, right? So training and running these models means huge numbers of processors plus cooling system and supporting electrical systems. So ultimately, that's an electrical demand problem, right? The key point for power engineers is scale and concentration. A large data center campus can be a very substantial new loads. And unlike many industrial loads, operators expect very high availability and continuity. So a utility fielding a large connection request has to look well beyond generation, transmission, and distribution capacity, voltage performance, short circuit levels, protection, dynamics, and contingencies. So, and there is also an interaction with renewables, adding large inverter-based generation and large concentrated digital load together means traditional planning assumptions may no longer hold. That's why AI data centers are power system engineering topic, not just a data center one. So let's break down what makes AI data center load different. So we have 4 characteristics. First, we have the scale. As a single large facility that can be significant load, and multiple campuses in one region can rival a major city load growth. Second, we have availability. These facilities need continuous power, continuous operation. So we can't afford even one fraction of millisecond of power interruption. So that's why we have to use UPS, batteries, generators, controls to help the system to be resilient in case of there is disturbance or grid failure. Third, we have power quality sensitivities. Like sags, interruption, and harmonics can affect sensitive computing equipment. Fourth, we have dynamics. So as we know that AI workloads can change electrical loading quickly, though this varies by architecture. So we should not assume every facility behaves the same. So that's our central transition generation is becoming more inverter-based and weather-dependent, while major new loads are larger and less tolerant of disturbance. So how do we study the combined system before we build it? That brings us to simulation. So engineering analysis is critical here. So we can't experiment on a live grid by creating major disturbances just to see what happens. Instead, we need to build resilient models. So for many questions, an RMS or phasor domain simulation is enough, like ETAP software or also Power Factory Silent. For fast interaction, power electronics controls electromagnetic transient, we need empty simulation, which is electromagnetic transient. And we use MCP and PSCAD software for this kind of studies. So let's look at what each gives us. So the idea is simple. Build a digital representation of the power system, which we call it single line diagram, to model our power system. And then test scenarios inside it. So that power system including synchronous generators, inverter-based resources, renewables, battery energy storage system, transmission, transformers, circuit breakers, loads, protection, and controls. So RMS simulation works at the system level. So it gives us like the bigger picture over cycles to seconds or longer. Good for transient stability, frequency, response, voltage behavior, and planning studies. However, empty which is stands for electromagnetic transient, goes deeper, modeling instantaneous waveform rather than phasors, valuable for inverter controls, switching behavior, fault response, and weak grid behavior over very short time scales. So I wouldn't say like neither is better. The right model depends on the question. If I'm asking, for example, how a larger system respond over several seconds, I would say RMS may be enough, right? But if I'm asking how an inverter interacts with the network right after a disturbance, I may need AMT. We will need AMT. That's why electromagnetic transient simulation, not optional anymore, is very essential and critical to assess and simulate our grid before it goes live. So in many real projects, both are complementary. So what does this look like in practice? So take a simple example, a sudden loss of generation. We recreate that disturbance in a model. That's what, as engineers, that's what we do, like on, I would say, like on daily basis. So we work on simulation tools, software. So, so for example, as I said, take a simple example, a sudden loss of generation. So we recreate that disturbance in a model, then change the conditions, right? And then we will ask these questions. What happens if renewable penetration is relatively low? What happens if it's very high, right? What happens when the system inertia is reduced? What happens when a large AI data center is connected? And what if the load is represented with a different dynamic model? And what happens if we add battery energy storage system or grid forming controls? So this scenario-based approach is powerful, and that's the purpose of using and mastering those the simulation tools, to be able to ask these questions, because we want to we don't want to look at we need to look at the risk, right, and see how we can prevent it and how we can help our system to be resilient during that grid failure, not to wait until the failure happens and then we ask, right? So this question should be asked before the system goes live. So this scenario-based approach is powerful. It lets engineers spot sensitivities before equipment is installed. So we can run contingencies, fault protection, voltage stability, frequency response, and inverter interaction studies. So the results drive practical decisions. Is a connection feasible and reinforcement needed? Is more storage or reactive support required? The control setting need to change? Could a grid forming resource help? Yeah, so let's pull the story together. Renewable growth brings real benefits, right? But also variability and intermittency challenges reduce visibility and more inverter-based generation. As the second generation retires, available inertia can shrink. So the disturbances can develop faster, raising the importance of fast response and advanced controls. On the demand side, AI data centers are creating very large, continuous, sensitive load. So the supply is becoming more electronic and variable, while demand is becoming larger and less tolerant of disturbances. That's why modeling matters. RMS for broad system behavior, AMT for fast power electronic for fast power electronic interactions. So together, let us de-risk decisions before touching the real grid. That sets up our next session, which will be on September 16. We move from the problem to part of the solution. Which will be battery energy storage systems. So as we know, the grid is changing and our metals have to change with it. So thank you for joining me today. And thank you again for being part of this first session. So the main takeaway I want you guys to take with you that the future grid is not just about adding generation or load. It's about how generation, demand, power electronics, controls, protection, and dynamics all interact. So so please use the question and question and answers, and I will do my best to get through as many as I can. Anything that we don't cover, I'm happy to carry into the next sessions. Thank you. Hi, can you hear me? Okay, yeah, I don't know where is the, yes. So you guys have any questions? Let me see the chat box. Yeah.
Okay. Well,
Yeah.
are there any questions on the side?
Is all clear?
Okay. I'm going to wrap it up. Can you just stop sharing? I'm gonna share and finish the slides. I want to share some few things with the attendees. Don't also log out. Let me know when to stop sharing. Able to stop sharing the.
Yes.
Okay, then I'll just share. I would like to thank all the attendees for taking their time for this session, and most importantly, I'd like to thank you, Hanan, for
Yeah,
this
thank you.
wonderful, informative session that we just gave now. And hopefully all the attendees took something from this session. And as we did say in the beginning that we will be sharing the slides on your email. So it's going to be sent to you in the next 2 business days, working days. So if it does not appear in your inbox, it should be in your junk folder, spam folder. And yes, I'm not sure if there's any other questions that we have from the attendees. Or there's a question from one Nash Titus. I'm not sure if you can see it, Hanan, the question. Or did
Yeah.
you answer the?
Yeah, how can we solve the grid challenge in power system? Yeah, Emmanuel. Yeah, Emmanuel has the question. Yeah, so the issue that was so by installing the battery energy storage systems and by using high fidelity simulation tools for like AMT simulation, and also understanding and mastering battery energy storage system technologies including grid forming control. So, so for electrical engineers, I see that most of them, they focus only on power side of the system. Now the control side is becoming very crucial for engineers. So you need to know about power electronics, also about like learn about Python, how you code, and also understand. So, and before moving to learning those technologies, we need to master our conventional grid, like the physics, the fundamentals of physics. Yeah, but for sure, battery energy storage systems, battery energy storage system control technologies, and AMT simulations are very essential nowadays to be able to solve those challenges. And we will look at those technologies in our next sessions.
Thank you very much.
Are you good, Emmanuel? Okay.
Hopefully he is. Just to touch on some of our upcoming programs, and we'll just take some few questions at the end. So these are some of the upcoming programs at ECT. On the left-hand side, these are the program names, as you can see, bachelors and masters, and the date are on the right-hand side. And for more information, you can also check our website. Our course advisors will then reach out to you and assist you further. And another thing that I wanted to mention is that we are currently running a promotion. So we, on the 3 months non-accredited professional certificate delivered by ECT's affiliated institute, which is EIT. So basically the promotion is for only a limited time. You can save up to £334 on our 3-month online professional certificate delivered, as I've said, by EIT. You need to enroll by 30 November this year, and you'll only be paying £599 instead of £933. So what I'm going to be doing now, I'm going to share the link for the promotion of the program. Those who are interested, they can click on the link and then claim the promotion prices for this year. So it ends, or rather you need to then enroll at least by 30 November this year. And I'm going to be sharing the link to the certificate of attendance now with everyone in attendance. So as I've said in the beginning, that it does expire after 48 hours. So you need to at least make sure that you claim it today, if you can, or tomorrow then, but it does expire after 48 hours. I've shared the link on the chat box with everyone for the certificate of attendance. Let me see. Okay, we can take a couple of questions. Anan, I'm not sure if you can see the questions, or should I read them out to
yeah,
you?
I'm just trying to.
Okay, I think there's a question
Yeah,
from.
so yeah, a good presentation. Thank you. But I would like to know how the integration solves the issue of power loss. Yeah, so as we know, like now our conventional grid, because of AI revolution, right? And AI loads that they are very critical, our conventional grid can't meet the demand. So we need to integrate renewable energy. That's very understandable, right? We understand that very well. But that integration represents substantial challenges. So how we can solve these challenges is by installing battery energy storage system. That's a must, you know. And as I always say, battery energy storage system, they are not, it's a good technology, but it's not just plug and play. So we have to master the control philosophy. you know. So that's one thing. And also, for example, our AI data centers, like that, they are critical loads. Because of the GPU clusters and AI training, they can't afford any power interruptions. So that's why we need to make sure that we have resilience control. And that's what I am currently developing for my Master of Engineering thesis, is that developing a continuous grid forming battery energy storage system control for zero interruption, for zero power interruption for AI data centers in case there is the power failure. Yeah, but we will look at these solutions and technologies in our next sessions. So in that first session, I just tried to give you guys like a broader picture about our modern power grid, and the main objective is to make a balance between our generation and demand, especially now because they are changing. Because our generation, we have renewable energy integration, inverter-based resources, and in our demand, we have AI data centers, AI load because of AI revolution.
All right.
Okay.
Thank you for answering that one. I'm not sure if we still have questions or it's just a comment. I think it's just a comment more than anything.
One is asking, when is the next session? So the next session will be on September 16th, the same time, and as today, and it will be on. Then we will dive deeper onto the solutions, like how we can overcome those challenges, right? So we will start with the battery energy storage system as a ultimate solution for those challenges. But when we talk about battery energy storage system, it's a huge topic, because this is my current focus, whether in school or work. So that's we'll talk about that in the next session.
All right. Thank you very much, Manan, for answering those questions. And we are at the end of the session. As I've said, I did share the link on the chat box, so please do claim the certificate of attendance. It does expire after 48 hours, as I've said. So there aren't more any questions I see. It's just praises to Hanan. I think, they're very happy. They're very happy about the session, it seems.
Thank you.
Which
Thank
which
you.
is a great sign. So hopefully you come back again on the 16th of September, as she did
Yes.
mention.
Thank you,
Um,
guys. Thank you.
Thank you very much. And thank you to all the attendees for taking their time to attend this session. I hope you did take from this session. We are done. So we are
Make
done
sure
for the
to
day.
follow along. Yeah, because it's a series of 5 webinars. And the first session is just gives you a broader picture, but make sure to follow along for the next 4 sessions. And I hope it will be very helpful for you.
Thank you once more, Hanan, and thank all the attendees. And we did have some technical issues, but it went all right at the end. Everyone is happy. I'm happy, and Hanan is also happy.
So this is the first session, so it's normal to,
Exactly, it does happen.
That's exactly what we need to learn. So that's exactly what's happened to our power grid. So we face challenges, but we need to be resilient, how to overcome those challenges. So that's part of life.
I couldn't have said it better myself. So we will see you on the next one. Bye, everyone, for now.
Yeah, bye. Take care.
Bye-bye,
Have a
Hanan.
good day.
Take care.
Good night. Bye.
Bye-bye.